interested in soft matter. That was a great work that you did. So let me talk about metastability in wetting phenomena, and this work has been developed with several people. Those Cristina, Yara, Davi, and Marion were my students, some of them are still students. And Alberto and Antonio are from Rome, and it was a collaboration with Marion when she was my PhD student with Alberto. Okay, so, well, when we place a droplet on a substrate, the droplet can display several wetting states. As you can see here, usually the way that we microscopically define those states are through this contact angle. And you see that the contact angle is small. It can be even 0 if the droplet is in the completely film. It wets completely the surface, as you can see in this example. But it can also have a very high contact angle. It can go from 0 to 180 degrees. And those states are hydrophobic, are associated with a hydrophobic state, and a state where there is no water wetting the surface. And the hydrophilic states are associated with the states that have small contact angle and the droplet wets the surface. So here we see two examples in which the water is colored, and then you can see them. You see that in this case, the droplet becomes almost a bubble, a ball, or a pearl. And in the other case, the droplet completely wets the surface. Okay, so there are several applications in this field. I'm just showing two of them here. Well, there is a lot. This is a lotus leaf, which I think the most well-known example of this phenomena, which is a leaf that's it's very hydrophobic. You see that the droplets of water they become like a pearl in the surface, and even if we move the surface, the leaf, you see that the water, it does not penetrate the surface. And then it's basically why we call this self-cleaning surfaces. There's another interesting application, which is the separation of water and oil. And among several properties that we can use to do that, here I'm showing the one that we use wetting properties. And you can imagine that you have a super hydrophobic surface, which repels water, but a oleophilic surface that absorbs oil. What one can do is that we can separate both, because as you can see here, you have a mixture passing through a membrane, and then you see that the water got separated from oil because the oil passes through and the water is retained. We have been working with this problem several years ago, in which we were studying through simulations and theory how to optimize the surface in order to obtain the best separation between oil and water. But that's not what I'm going to comment in this talk. What I want to concentrate today is about the metastability of the contact angle, which is a very common phenomena in this subject. And what you see here is an example, an experiment in which a droplet of water is placed carefully on the surface. And then, as you can see, it displays a high contact angle. So it's in a hydrophobic state. You know, there is no water penetrating the surface. You can see that there is a light passing through the droplet. And then a droplet is released from a given height, and then it acquires some kinetic energy, and it's able to penetrate the surface. And then you see that the contact angle is smaller than in that case, meaning that depending on the initial condition, one has different final states. And this metastability is interesting for several reasons. One of them is that several applications require the metastable state because we very often want to be in the hydrophobic state. It also implies that you have a high hysteresis in the contact angle because depending on the way that you place the droplet, you observe both. And of course, it implies that you have a difficulty in predicting the contact angle because it's not unique. And then you need a theory that is able to predict more than one. Okay, so in this talk, what I want to concentrate in the first part is an example where metastability is quite relevant because it's actually, which is the case of a particular case of fractal structure. And I'm going to speak about that in a minute. And in the second part, I want to focus in an example where we can compute the free energy landscape of those surfaces, and then to understand what does those metastable state looks like and what they mean. Okay, so here what you are looking again is the example that I have spoken in a few minutes ago about the lotus leaf. And if you want to do a zoom in this leaf, what you see is that there are bumps. And if you do a zoom in the bump, you see a second layer of bumps, which means that this leaf has roughness in multiple scales. And this is quite often in nature. When the material is hydrophobic, it's a common feature. And then, based on the fact that it happens very often, engineers and physicists, they started reproducing this characteristic in the laboratory. And this is one of the first papers in which they show this experimentally that fractality really matters in this field. What I'm showing here is a droplet on a flat surface, and you see that the contact angle is around 100 degrees. However, when they take the same chemistry of surface and they do and they are able to make a fractal surface, the contact angle increases by a great factor, meaning that fractality implies is very important for hydrophobicity. And then what we wanted to do is to quantify the influence of fractality, and then we proposed a very simple hierarchical model in which you have the surface in the first, at the n equals 1, the first level, one has pillars, and then we create, let's say, holes in the pillars and have a second order, and then you create holes here and have a third order, a third level, and so on and so forth, and then you have n levels of hierarchy in the surface. And well, one can define two different geometric parameters which are important in the field. One is the aspect ratio, which is basically the height of the structures over the width. In the case of a pillar, is a very well-defined quantity. And the second importance is the solid fraction, solid liquid fraction, which is phi, and it is related to the area that a droplet sees over the total area of the surface. And then with those, we proposed this toy model. And we asked how the energy and the contact angle of the wetting states change when the level n increase. And then we proposed a simple model in which we are able to compute the energy of the states and the contact angle. And we proposed two different states. One is the hydrophobic state. You see that there is no water filling filling the surface. We call this Cassie-Baxter very often for historical reasons. And the other states, it's a hydrophilic state, a Wenzel state, as well for historical reasons. And in this case, you see that the surface is wet, let's say homogeneously wet. And then the model is just counting the energy of creating interfaces between the liquid and the air, and the liquid and the solid and the air. And I don't want to go into details of these equations, but just to tell you that we are able to compute for any level of the surface the energy of that state and of that state. And it does depend on the geometric parameters of the surface and the chemistry, on the geometric parameters of the droplet. And then what we can do with that is that we are able to optimize, let's say, to find the minimum energy state for the hydrophobic state and for the hydrophilic state. And for that state, we know which is the contact angle. And then we compare which one is the least energetic, and we can create a wetting diagram. And what you see here is for n equals 1, so actually n equals 1 means that we are in this pillared surface. And what you see is that we find a transition line which separates the two sides of this wetting diagram. One is when the droplet prefers to stay in the hydrophobic state. And the other side here, the droplets, the preferred configurations is the one that is in the hydrophilic state. And then what you see in color are the angles, the contact angle of the droplet, if you want to place the droplet in the surface. And you see here, I didn't say it, but this is a model where we take the same aspect ratio and the solid, the liquid fraction for all the levels, just to be simpler. And so what this wetting diagram means is that if I take a surface with 0.665 and there's, let's say, A equals to 4, the surface is such that the droplet would prefer to be in the hydrophobic state. Okay, so then what you said is let us increase the level of the surface, you know, the level of the hierarchy, meaning that we would be in that type of surface. And what you see is that, first of all, for the same droplet volume, what we see is that the transition line is basically untouched. It does not change, meaning that we could think that increasing the hierarchical level would change, let's say, would improve, would increase the size of this phase, because you observe in nature that fractality implies more hydrophobic states. But that's not what happens. The transition line does not change. However, the contact angle, they do change. Let's say if we are using the same color code here, then let's say for surfaces which are 0.25 and A equals 8, now in this surface the droplet would have a much higher contact angle. But then the question is, why then the droplet increases? Why the fact that increasing the hierarchical level would change the angle if the line does not change? And then we tested the metastability hypothesis, which in the sense that we tested if there is some dependence on initial conditions. And what we did was to consider a model that we use quite often, which is with the three-state spot model. And what you see here is an slice of a 3D droplet. We cut it in boxes, and then for each site or each spin, we assign, let's say, a number. Let's say for water is 1, for air is 0, and for the surface is 2. And we create a Hamiltonian which only takes into account the energy, the interface energy. So for example, if we take two neighboring sites of different spins, let's say 0 and 1s, this would cost an energy, you know, because this delta would be 0, so 1 minus 0 is 1. Then we would add some energy. But if you would consider two neighboring sites with the same type of spin, this would not cost any energy. So this Hamiltonian is just counting the energy of creating the interface. And then we do a very simple, we apply the Metropolis-Hastings algorithm by swapping two sides of the interface. And then what we do is that to test the metastability hypothesis, we use two different initial conditions, one in which the droplet only touched the surface, which is a very hydrophobic initial condition, and the one that the droplets completely wets the surface. Not completely, but it stays in this configuration. And then what we observe is the following. Depending on the initial condition, that's an example of the final condition that we find. Don't pay attention in the black and the red lines. That's not important for this talk. What we see is that, for example, for this point, which is this point of the diagram, starting at this state, the final state of the droplet would be that one with a given theta c that I'm calling theta c of this initial condition. And starting at this state, the final state would be completely different, would be the one that the droplet is not penetrating the surface. And then what we do is that we subtract this angle and this angle, and then that's what you are looking at in this diagram. So for example, if this quantity is 0, which happens far away from the transition line, what this means is that there is no dependence on initial conditions, because we start in different initial conditions, and then the final state would be the same. And this is what happens far away from the transition. But close to the transition line, what happens is that the final states can be quite different. As you can see here, the difference can be as big as 100 degrees, which says that those type of surfaces can present a very high metastability in the sense of the dependence on initial conditions. So actually, what this work shows is that the increase of theta c with the N, which is in this case, the hierarchical level of the surface, is not a result of the thermodynamics, but actually is the fact that those wetting states are metastable, meaning that very likely in the nature, the reason why the surfaces are hydrophobic is because the states are metastable, and not because they prefer to stay in that state. Okay, so let me now turn a little bit for the case where we want to describe those states, and to do that, we will compute the free energy profile of the surface. And let me just come back a little bit to the example that I have shown before, in which we have the experiments in which the droplet the final state of the droplet depends on the way that we place a droplet on the surface. And the way that we rationalize those type of things in physics is usually by thinking about complex landscapes in which there are several local minima. In this case, I'm just showing 2 minima. In that case, this state is the metastable one, so actually the hydrophobic state is just a local minimum of the landscape, and this would be a global minimum. And then we want to compute the free energy, but just remind you that there's a challenge in doing that, because when you do a Monte Carlo or even dynamic simulations, what we do, if the simulation is correct, is that we look for, what we can do is that we sample configurations which are at the minimum. Depending on where we start the system, we can reach that or this minimum, but we cannot reach the whole landscape, except if you force the system passing through all of those states. And to do that, there are several techniques. The one that we use is the restrained Monte Carlo, in which we take, again, the Hamiltonian that I have just shown before, that only takes into account the energy of creating states. And what we do is that we add a term, constraint term, or a restrained term, which depends on F, and F is the fraction of water that wets the surface. So all the water that are below the surface, we count, and then we say, okay, let's give us a target fraction which oblige the system to keep some water below the droplet, and of course then you have to take the system, this term out in order to compute the free energy, but we know how to do that. And then we find the free energy state, the free energy landscape of the system. Okay, so let me show you what we have discovered. Okay, so it's now. So now we are doing for the simpler system with simpler substrate, which is the pillared one. I'm calling S1. I'm not changing the width, neither the height. I'm only changing the distance between pillars. So for this first example, the first movie that I will show in a minute here is for a surface that has a small, let's say, distance between pillars, and then I will compare it with the one that has a little bit bigger. What you see here is that the free energy landscape is such that depending on the filling below the droplet, it only displays one minimum. And what you see, let's show what do the minima correspond to. Okay, let me stop for a while. This is the first minimum and the only one. And you see that the droplet is not filling the surface. So the hydrophobic state in this case is unique, and it's the global minimum. And then we keep doing the simulations, and you see that the droplet wets the surface. And then we find some states which are where the system is in the hydrophilic state. But you see that the energy only increases in that case. Now, let me show another geometry in which we see that the landscape is much more complex. One has several minimum. And what we see here is that, well, there is one minimum. The first minimum is again a minimum. Oh, no. No. Now, let me show again. So, okay. The first minimum is the one that the droplet is again in the hydrophobic state. But you see that the hydrophobic state in this situation is not the global minimum, it's just a local minimum. So it's a metastable state. But then if we allow the system, if the system, the water fills the surface, we see that the order minimum are such that the droplet is continuously wetting the surface. No. And let's say the global minimum is the one that wets a given number of grooves. And then it keeps on going. And for the other states, what we see is that the energy always increases. Okay, so let me just summarize. No. Now that I want to pass, I can't, but okay. So this is just to summarize what I have just shown, that this is for the first surface with a smaller distance between pillars. This is for the highest distance between pillars. And what I have shown you is that for the surface S1, there is only one single minimum, and the single minimum is hydrophobic, and it's unique. And for the other geometry, the hydrophobic state is still present, but now a metastable state. And then you have several hydrophilic states. Some of them are again metastable because they are the local minimum. And then you have one which is the global minima. And then you see that this type of surfaces, it has the metastability of the contact angle, and it presents a hysteresis of the contact angle. And just to summarize again this, and the fact that, because one can have in this type of surfaces several minimum, and then metastable states, it also implies a dependence on initial conditions, because then we have tested in our system to start with 3 different initial conditions. And in that case, where in the surface, when you only find one hydrophobic state, what you see is that we can start at any point of the phase of this complex landscape, and the droplet always finds a given minimum energy state. But in the surface of type S3, we did the same numerical experiment, and you observe that the droplet finds different final conditions. Just to say that, as we know, the fact that you have this complex landscape that now you can describe a little bit better implies this dependence on initial conditions. Okay, so just to conclude, metastability is a very common feature in this field, and then I have shown you hierarchically structured substrates. The wetting states with high contact angles are metastable. And then I explained a work that in which we computed the free energy profile, and I have shown that depending on the geometric parameters, one can have this, the several minima, which implies then a dependence on initial conditions. And finally, the implications of those findings is that one of the implications that the theories that only predict one contact angle cannot be correct or cannot be complete. One needs to build some theories perhaps inspired in the wetting states that we are able to look at in simulations. And then a possible application that I would like to do one day, but I'm not doing yet, is that one can think about when you want to create, to use a surface a state which is metastable, one can think about how to increase the barrier between the states, between the metastable states, and then perhaps, with a very high barrier is enough to keep the state that we want to have. So not necessarily to have a thermodynamic minimum, but you can actually play with the metastable states. And with this, I close my talk, and thank you.
Thank you, Carolina. So we have time for questions.
Hi, Carolina. 2 questions. First, are there some experimental results for comparing with your theory?
Yes,
Sorry if you showed and I didn't pay attention.
No. I mean, I haven't. The only experiment I showed here about metastability is that one that This is a real experiment that I presented, which is as a dependence on initial conditions. And then you have, it's a very common, really a very common feature depending on the a lot of surfaces do present dependence on initial conditions. They do present metastability of the contact angle. And actually, this is a problem, for example, when we want to, one of the applications in this field is to capture water from the atmosphere. And then we want to avoid, for example, this dependence, the difference between the contact angle. We wanted to reduce that. So there are applications in which you need to know that.
Okay, so a second question is there some influence of the temperature?
Well, some papers, they study experimentally, and one that comes into my mind is that, well, let's say temperature does not play a role in order to, let's say the barrier is much bigger than KBT. You know, you need to shake the droplet in order to bypass a barrier, because it's a the droplets are microscopic. But what you can imagine is that you can put temperature and then the droplets evaporate. And it's known that there is a phase transition, there is a transition of the wetting states when the droplet decreases its volume. So you see when the droplets evaporate, then you can pass through from the hydrophobic to hydrophilic state. But it's due to the fact that it depends on the volume.
Hi, thank you for the wonderful talk. I'm just curious, how this contact angle is measured in the experimental? This is
the contact angle?
Yeah.
Well, you take a picture of the droplets, and then you do this in ImageJ or in any.
Yeah.
It's
okay.
I mean it's a well-defined geometric. You know, I can tell
it's
you.
From the picture. Is the
Yeah. It's a really, in this sense, it's a quite easy field because it's a microscopic one.
Okay, and you in your simulations you play with the size of the droplet?
Yeah, not in that one, but in a previous work we have played with that, and we played with the fact that the droplet changed its volume, and we have shown the transition that I was just mentioning, that depending on the volume, one observe that the hydrophobic phase decreases, because the droplet, by decreasing the droplet, it can, let's say, basically fills the surface, which is, I think, it's a very geometrical problem.
Okay, thank you very much.
Thank you, Carolina. So, quick question. You presented calculations for this hierarchical structured surface.
Yeah.
What do people observe in terms of the contact angle dependence on the roughness of the surface? Like, let's say you took a disordered sort of surface. Would you see something similar with hysteresis? Does it have to be fractal-like with that? You know,
yeah,
or a disorder, if that sort of smaller scale actually matters?
Yeah,
I'm just curious.
Well, no, you can have, let's say, you can have metastability without hierarchical structure, as I have shown, for example. One can have a hydrophobic state without fractality. So basically, roughness, it matters a lot. So for example, if you have what is quite known in this field is that chemistry is important. But then if you have a flat surface with let's say you put a droplet in this flat surface, and it presents less than 90 degrees, which means a hydrophilic state, and you put roughness, then you increase the fact that it's going to be more wet. So basically, the roughness, it tunes the hydrophobicity. You know, it would enhance the hydrophobicity. Of course, there are other effects, but I'm just telling you the basic. So yes, the fact that you have studied the fractal surface is just because it's a very common feature in real systems. But you can find the phenomenology without that. Exactly. Yes. Yeah.
Well, thanks, Carolina. Lovely talk. I just want to see if I have the right intuition about what stabilizes locally the hydrophobic metastable state. I assume it's because for small deformations, you're increasing the water-air interface.
Yeah.
And until you overcome that barrier and start getting water substrate.
So that's basically the difference between the energy, because, well, you need to think about that's the energy between the air and the water. That, you have some air and water below, which means that you create some interface, which is less energetic than if you would be completely wet. For this type, but then when you increase A, then it changes a little bit because it would be less energetic to be completely wet, although locally you still have some ways of keeping your droplet there, without filling the whole surface. That's the way that I think as well about that.
A quick question. Oh, I was thinking, but I couldn't find an answer. This is 2D, right? I mean, it's one-dimensional, then you have the energy here.
No, that's 3D.
Yeah,
I was only showing the. Yes, it changed a little bit.
Yeah.
There are some studies in 2D, but then the physics a little bit different because, in 3D, you can imagine that once the droplet wets the surface, it finds some paths to continuously wetting the surface. Mm-hmm. But then in 2D, you need to bypass the growth at each time. So the barrier is essentially different. Mm-hmm. So yeah, the physics is a little bit different in 2D.
Okay, thank you.
Okay. So let's thank Carolina again.
Okay, you can.
Sorry, I didn't realize there was one last question.
Thank you so much for your amazing talk. I have a question if you have studied this free energy profile with an n greater than 1.
With what?
With an n greater than 1. With a
no. Yeah, actually, I have shown the work in a different order, but the one with the pillared was made before, and we have not tried to see if it would be interesting to see if they have more metastable states or if they are deep. Yeah, but we haven't tried yet.
But is there a reason why, or?
No, just because it's much simpler to, we start with the simpler type of surface, which is the pillared one. That's the reason.
Thank you.
Okay, now coffee break time, and once again.